Okay, this is going to be our fourth video in our magnetic fields and magnetic forces series. In this video, we're going to be covering all the content from section 27.6. We're going to be talking about magnetic forces on current carrying conductors. Okay, and so we'll get started here. So to carry or to calculate the force on a current carrying conductor, we're going to start by looking at our magnetic force equation, right? Remember the equation here that we talked about a couple of videos ago and have been using on and off. The figure below is going to show us how sort of a single charge moving across a wire of length L that has cross-sectional area A would sort of experience force, right? And this is just an application of that equation. So we have our current carrying conductor kind of like this. We have some current going through like this. But if we zoom in on a single charge moving through our conductor, it kind of looks like this. It has a drift velocity in the upward direction here. We have a magnetic field going into the page, as is indicated by these little X's. And so if we think about it, we can place our right hand flat on the page. Our fingers are going to be pointing in the direction of the drift velocity. And if we curl our fingers into the page toward the direction of the magnetic field, our thumb points in the direction of F. And that's the direction that we're going to have our magnetic force, right? So our current, since the positive charge is moving upward here, the current is also going to be moving upward, and it's going to be moving with a, well, all these charges are going to be moving with a drift velocity of Vd, right? And so we can kind of take a look at what the magnitude of this force is going to end up being, right? Because we look at our magnetic force equation. We have that here. The velocity is going to be replaced by the drift velocity, so the velocity of each of these individual particles as it's all moving as one sort of big column upward in this direction, in the direction of our current. And then since Vd is perpendicular to B, right? We have Vd going upward and B is going into the page. So they're perpendicular, so the magnitude of our force is going to be given by Q VdB, okay? And so we have the magnitude of that force. Using these ideas, we can derive an expression for the total magnetic force on all the charge moving in this wire of length L, right? So we're thinking about all this charge moving. When we think about a bunch of charge moving together down a conductor, we're thinking about a current, right? So if we look at the length of this thing, it's a length L. It has a cross-sectional area A, and we're now going to let the total number of charge per unit volume be N, okay? And the volume itself of whatever chunk of conductor we're looking at is going to be A times L, right? Because A is our cross-sectional area and L is the length of the wire over which we're looking at this. So if we have the number of charge per unit volume and we have the volume, if we multiply the two of those together, we end up with the number of charges that are contained in that volume, right? So NaL is going to give us a number of total charges that we're moving up that chunk of conductor of length L, right? And so if we take the force on a single charge and we multiply it by the number of charges we have, well, we're going to get the force on the full conductor. All those charges are moving. All of them are going to contribute some force. And so this expression in equation 1 here is the expression that we get for the number of so I'll point to each of these things and sort of mention what they are. This is the number of charge per unit volume. These two give us our volume, so the whole thing gives us the number of total charges moving times the charge on each of them, just the value Q, times the velocity that they're moving at, the drift velocity, right, times the magnitude of our magnetic field. Okay, so we now have an expression for all that moving charge, but really we'd like to write this in terms of a current, because when we're talking about a current carrying wire that's obviously moving charge down the wire, we refer to things in terms of currents. We don't refer to things in terms of how many individual charges are moving down the wire, right? So if we remember back from chapter 25, we can write our current density in terms of the number of charges per unit volume times the charge of each of those charges times the velocity, because we have that's how much a volume is being moved down the wire, right? Because depending on how quickly this clump of charge is moving down the wire, it'll dictate how much charge per unit volume you have, and this is a charge per unit volume. If we multiply the charge per unit volume by A, by the cross-sectional area of this thing, we end up picking up our current. Okay, and so if we just make these two substitutions into the expression that we have above here, three of these variables turn into J, and then J and A together turn into I, and so we end up with this expression here. F, the total force experienced by the wire, is going to be equal to the current running down the wire times the length of the wire times the magnitude of our magnetic field. Okay. Now, if B, so all this was generated using this setup up here, right, where B is perpendicular to our wire and to our current. But if B is not perpendicular to the wire and so not perpendicular to the current, we have some angle between B and I, and just like we did in the case of our force equation for a single charge here, our magnetic force equation for a single charge, we can sort of incorporate that angle, and then what ends up happening is we're only really interested in the portion of B that's perpendicular to the wire, and so we can write it in terms of the sine of the angle phi, which is the angle between B and our length segment L, right? So we end up with this expression here. But this really looks very, very much like our earlier expression for our magnetic force on a single charge. But we have to remember that we were able to then sort of write this expression with a sign in it. It's really just sort of hiding a cross product inside it, right? So if we consider cross products, it then allows us to write down the expression as a full vector expression like this. So this is really the sort of expression we want to take forward for the force on a current carrying segment of wire, right? So the way this is going to look is it's going to be I, which is the current, and then it's going to be L as a vector. This is L as a vector because it's the length segment of wire, and it's a directed segment in the sort of direction of our current, right? And it's going to be crossed into our magnetic field, which is also a vector quantity, right? So basically, just to read through it again, we have the magnetic force on a straight wire segment, okay, which is carrying some current I of length L in a magnetic field B. So we simply calculate it by taking I, and then it's L cross B, okay? And so just like we had a right-hand rule for all these single charge situations, the right-hand rule also works for all these current carrying situations. So we have a bunch of different diagrams here. They're all right-hand rules, and it's kind of a nice way to sort of remember what direction things are going to point in. So let's say we look at this first diagram here on the left. If we place our hand sort of on the wire in the direction of the current, right? Let's say you place your hand like this is like my hand. Imagine. So you place your hand like that, right? Then you're going to have to kind of twist it sort of upward so that you can curl your fingers in the direction of our magnetic field. But if you do that, then your thumb is going to be pointing upward, and that is the direction of the force on the wire. Okay, so that's the same idea in every case. You kind of make your hand like a flat palm, like a karate chop kind of like hand thing. Place it on the wire in the direction of the current, and then whichever way you have to orient it so that you can curl your fingers in the direction of the magnetic field, that means your thumb will be pointing in the direction of the force. You can see it here. Hand, fingers curl this way, thumb has to be going upward. Here, hand's going to be this way, but you're going to have your hand kind of pointing sort of downward to be able to curl your fingers in the direction of the magnetic field. It's kind of hard to see it from here, but you can kind of imagine like lifting your arm up in the air and placing it so that the edge of your index finger is sitting on the wire, and then you have to curl your fingers toward B, and so your thumb will be downward in that case. Same idea over here, right? You're placing your hand on I, curl your fingers toward B, your thumb must be pointing upward. Okay, and this is all right hand, right? So it's all the right hand rule. Okay, so that's kind of this this equation here, 27.19, is definitely one that we're going to want to remember. That'll be on the formula sheet. But what happens if our conductor is not a straight line, right? Like, let's say we're not dealing with a straight wire, it's some sort of a curved wire. What do we do in that case? Well, we can break up all the tiny little individual contributions to our force. We break them up into DFs, and we break up all the tiny little length segments that make up the wire into DLs, as you can see here, and then simply we're just going to integrate over the whole contribution of the wire, right? So we're going to integrate over all these little DL contributions. Well, we're going to integrate over the whole thing, and there's a cross product in there, so we'll have to be careful how we do it. But basically, we integrate over all DF to pick up the full contribution to F, and in doing that, we'll have to integrate the right-hand side here, which simply will have us run across all of these tiny little length elements, all these tiny little DLs, to build up the full length again. Okay? And so those are the new concepts that we're going to be introducing in this section. I'm going to do two examples now. The first one's not too bad. The second one's a little more involved, but it's not too bad also. They'll take a little bit of time, but we'll get into them here. Okay, so this is 27.7 from the text. It's a magnetic force on a straight conductor. And let's get started here. We have a straight horizontal copper rod, carries a current of 50 amps from west to east. Okay. This is in a region between the poles of a large electromagnet. In the region, there's a horizontal magnetic field toward the northeast. Okay, so 45 degrees north of east, with a magnitude of 1.2 Tesla. Okay, and in part A, we want to find the magnitude and direction of the force on a 1 meter section of the rod. And in B, we want to find what would happen if while keeping the rod horizontal, we want to know how should we orient it to maximize the magnitude of the force, and what that force will be in that case. Okay, so when I first read this, as I was putting this into the slides here, it wasn't super clear, so I'm going to kind of like draw it out, and maybe we'll see what they mean by this. Okay, so for part A, it's not too bad. For part A, we have how much space do I have? Not much. Okay, I'm going to write real small here to try to get it to work. Okay, so for part A, we have a wire that looks kind of like this. We can imagine. And they use their coordinate system in kind of a weird way. They talk about north, east, southwest. So we're going to have like a little wind vane thing here. This will be north, south, east, west. Okay, and so our wire runs west east, right, from west to east, and then we're going to have 45 degree north of east is going to be our magnetic field. So we can imagine this is like west east, and then we have a magnetic field that runs like this. Okay, where this, call it theta is 45 degrees. Okay, and so we're interested in the force that 1 meter long of this. So this is going to be our L, and the magnitude of L is going to be 1 meter. Okay, and we're also told, okay, so this is B, and the magnitude of B is 1.2 Tesla. Okay, and I guess just to be complete, we have some I running in the wire in this direction, and I is going to be 50 amps. Okay, so we want to calculate what the force on that 1 meter section. So what the force on this, if we're calling that L, what the force on that 1 meter section of wire is going to be, right? And this we can pretty much just pull right out of the equation. If we scroll up a little bit, we'll see that F is equal to I L B sine theta or phi or whatever. But in this case, we have theta, so we'll just use theta. So we can just substitute in numbers at this point. This is not too bad. We have 50, and then we're going to have 1, and then we're going to have 1.2, then we're going to have sine of 45 degrees. Okay, and if you do that calculation, you're going to find 42.4 newtons is our force. Okay, that's the answer to that part. Now, in part B, the way they worded this is a little bit strange, but what they mean now is, if you look at our drawing here, we wanna keep the rod horizontal. So what they mean by horizontal is keep it in the plane. Well, okay, maybe I'm gonna draw a coordinate system here so I can talk about direction. So let's draw a coordinate system that's not north, south, east, west, but I'm going to superimpose on top of that an x, y, z coordinate system. Okay, so imagine this is x, this is y, and then coming out of the page, like a dart coming towards us, that's going to be z. Okay, so they want to talk about now. They want to talk about how you could orient this thing by keeping it in the xz plane. So basically spinning it so that it's still not pointing up in the y direction at all, but it's in the xz plane, such that you maximize the force on the wire, right? So you're free to spin it sort of like upward out of the page, or in the sort of k-hat direction here, in the z direction, such that we're trying to maximize the force on it, right? So if we're going to be turning it like this, well, first we want to probably, here, let me do this. First we want to write down what our B is, right? So we know that our magnetic field B is 1.2 Teslas, and it's kind of pointing in a little bit in the x direction, a little bit in the y direction. It's actually 45 degrees in each of those directions, right? And so if we write it down like this, we can see we're going to end up with an expression like this. Okay, so really that is what our 1.2 Tesla magnetic field kind of looks like, right? It's partway in the I hat direction, partway in the J hat direction, and if we let this angle vary, like imagine this 45 degrees is theta. If we cranked it all the way down, then it would be fully in the I hat direction, and cos of 0 degrees is 1, and so all of it would be in the I direction, right? Or in the I hat direction. And if we cranked it all the way up so that it's pointing straight up, then sine of 90 degrees is 1, and it's all the way in the J hat direction. But the way it is now, it's halfway between the two, so it has the right magnitude, and this is the direction it's pointing in, right? We still have I equal to 50 amps. We still have our magnitude of L equal to 1 meter, but the question now is, what's the direction in 3 dimensions that we're going to be able to point our L, our 1 meter length of wire, such that we get the maximum magnetic force exerted on this section of wire, right? And so this could, in principle, be a somewhat complicated problem, right? Because how would you do this if you were just trying to sort of plug and chug and go through this? Well, you would set up another angle, and it's hard to draw it here, but you have to imagine that, like, imagine that the z axis is kind of coming out of the page like this. You'd have to draw an angle between the x axis and the z axis, right? Like kind of keeping this in mind, because you're going to want to rotate this thing away from the x-axis a little bit toward the z-axis and find the angle between the two of them where you're really getting the maximum contribution of the force on the wire. So you would need to write L as a vector, like 1 meter. It's going to maintain that 1 meter length, but it's going to point in the cos, and I'm going to call it phi. Let's say we call this angle phi. It's going to point cos phi I hat plus sine phi k hat, right? Because it's coming up toward the k hat direction, and we want none of it, and we're not allowed to turn any of it into the j hat direction, right? Because we're told it has to stay in that xz plane. That's what they mean when they say keeping the rod horizontal. Okay. So this is fine, except that we would need to solve the equation. We would need to basically maximize the equation F equals I L cross B for this. So you would end up having to maximize I, and then I'm basically just going to write down L cross B, but look at each term, right? We have to remember that as we're going through here, some of these terms, like for example, and this is probably something that that we all want to have sort of memorized, like I cross J is equal to K. These are all hats, right? K cross I is equal to J. J cross K is equal to I. And if you flip these, if it's J cross I, this is equal to minus K hat, right? And if it's I cross K, this is equal to minus J hat. And K hat cross J hat is equal to minus I hat. Okay, and all the rest where you're multiplying by itself, like I hat cross I hat is equal to 0, J hat cross J hat is equal to 0, and so forth, right? So when we actually do this cross product, we're going to have a lot of terms that don't go to 0, right? We're going to be crossing L into B. So yeah, so the cos phi and the cos 45 I hat are going to go to 0, right? And these are just root 2 over 2, right? Sine and cos of 45 degrees is just root 2 over 2. So you're going to end up with something that kind of looks like this. You're going to end up with an I, and then you're going to have, okay, so these two are going to cross and cancel out, but then you're still going to have cos phi I hat cross root 2 over 2 j hat. So you're still going to have root 2 over 2 cos phi I hat cross j hat plus, then you're going to have terms that come from the k hat crossing into things. So you're going to end up with a root 2 over 2 sine phi, and it's going to be k hat cross I hat. And then you're going to have another term. Do I have space here? I'll finish it off here, yeah. So root 2 over 2, and now you're going to be having k hat cross j hat. So you're going to have sine phi k hat cross j hat, right? And so what you would need to do is solve all this, and we can take it a little bit further, but we're going to find that we can't actually numerically or analytically solve this. We would need to do it numerically. So we can kind of rewrite this. We have an f, which is equal to, I'll take it one more step further here. So we'll have I'm going to pull out a root 2 over 2 here, root 2 over 2, and then we're going to have cos phi I hat cross j hat, well that's k hat. Then we have this root 2 sine phi k hat cross I hat, well k hat cross I hat, that's j hat. And then we're going to have another sine phi and k hat cross j hat. Well, k hat cross j hat is minus I hat, right? So I'm going to put I hat here, and I'm going to switch this to a minus. Okay, and so we need to basically solve for the phi that's going to maximize this. But this is not a super simple situation, right? Because we still need to get the magnitude of this. So we're going to have to dot it into itself, right? So you're going to end up having to take f dot f square root to get the magnitude of f, and then maximize that. But we don't need to do all of this is basically the moral of the story. You may need to do all of this if the question sort of asked for it and there wasn't a very simple way to figure out what the answer was. But we're looking for the maximum possible value. We know the maximum possible value is going to happen when the angle between our B and our L is 90 degrees. Okay, and there's only one angle that's going to happen for, and we don't even need to know what that angle is because we're only asked what the magnitude is. So we can basically skip all of this, and you may not always be that lucky, so you may actually have to go through all these steps and then dot the two of these things together and end up with some sort of a nasty situation where you have to solve for phi, but phi is buried in a bunch of trigonometric functions and you can't get to it, and you have to solve it numerically or something. But because we know that this is going to be maximized at 90 degrees, well, we can just right away write down f equals IL b sine 90 degrees, right? This is just 1. And so f is just going to be ILB. And we know what all these are. We know what I is, this is 50. We know what L is, that's just 1. We know what B is, that's 1.2 Tesla. You do the calculation, and this is just going to be 60 newtons, right, is equal to F. So that's the magnitude of the force that we're going to have if we orient this thing correctly. And the answer to how it should be oriented, well, it's such that B and L are perpendicular to each other, and there is only one value for which B and L are going to be perpendicular to each other. Well, that's the value in which we have the L pointing directly in the Z direction. Why? Because B points a little bit in the X and Y direction, so we know it sits in the XY plane. It doesn't point at all in the Z hat direction. So if our L points in the Z hat direction, then automatically you have a 90-degree angle, and that's the only direction for which you can have a 90-degree angle. Okay? So that would be the answer to that one. Okay? Now in 27.8 we have a little bit of a messier situation here. So let's take a second and just look at the diagram, or maybe I'll read through it first, then we'll take a moment and look at the diagram, then we'll actually do the calculation. Okay? So 27.8, we have a magnetic force on a curved conductor. Okay? And let's really take a look at what's happening here. So this little circle with an X in it means that we have conductor running into the page here. Okay, so you can imagine that the conductor runs from like behind the page up until it hits the page here. Then it goes around this loop, and then it continues off to the left here until this point for some length L. Okay. So reading the problem now, in this figure below, the magnetic field is a uniform magnetic field, and it's perpendicular to the plane of the figure, so perpendicular to the page. It's like pointing out towards us, right? We see the dots, they're like darts heading towards us, okay? And so the conductor is carrying a current I, and it's sort of carrying it to the left here. So it's carrying it like up the wire toward us while it's here, and then it's carrying it around this loop, and then it's carrying it off to the left, right? So like up toward us, then around the loop, then over to the left. Okay, it all has to be going in one direction. That's how we know it's coming up this piece of wire that goes down into the page. The wire has three segments, as we talked about. Section 1 here is a segment of length L that's perpendicular to the plane of the figure. So this section here that points into the page, that's length L. Section 2 is a semicircular chunk here. And section 3 is another straight segment with length L that's parallel to the x-axis. We see it kind of leaning over here. Okay, and we want to find the total magnetic force on this conductor. So it's a little bit messy here. We can probably fairly easily think about how we get the forces from the two straight sections, right? So that's what we're going to do first in both cases, and then the curved part, we're going to have to use these infinitesimal little contributions to our force, these dFs, which are going to be built up out of these dLs, and we're going to have to integrate over that semicircle. Okay, so let's get started. I'm going to try to leave some of this on the page. So what are we looking at here? Well, first thing, let's write down our B in terms of its magnitude, which is B, and its direction. The B is going to be pointing in the k hat direction, kind of out of the page toward us. Okay. We have F1 and F3. Those are going to be the contributions from F1. We'll call this part that's kind of buried in the page the F1 contribution. This is going to be the F3 contribution. Okay, so these are straight lines. Okay, and then the F2 contribution is going to need to be integrated. Okay. Okay, and then once we have F1, F2, and F3, then we can simply say that the total F is going to be F1 plus F2 plus F3, the vector sum of those three contributions. So we'll start off by looking at contributions 1 and 3 because they're over straight wire, so it's not too bad. We've done that before. So let's look at section 1. In section 1, this part that's pointing into the page here, or pointing out of the page in a sense, that the wire goes into the page, the current would be running up that wire and then hitting the page and then going around this curve, right? So our L1, our length 1, is really going to be magnitude L pointing in the k hat direction, right? The current is coming up the wire, so we can think of the length vector pointing towards us, okay? This means that F1 is really just going to be equal to I, L cross B. And since we just wrote down what L is and what B is, well, we can see that right away we're going to have the cross product K cross K, right? We're going to end up with I, L, B, and then their directions, K hat cross K hat. Well, that's 0, and so this is 0. Okay, so this is our F1. Let's take a look at what happens over here on the side, on the left-hand side over here. This is our section 3 contribution. So we're going to end up with our L, let's call it L3, is going to be equal to L, and what does it point? Well, it points in the negative I hat direction, right? So it's going to be negative I hat. And so what does this mean? Well, this means that our force on our section 3, this is going to be, oops, there should be an equal sign there, it's going to be I, L cross B, where this L is L3, right? And this L here was L1. So if we do that, we're going to end up again with the same leading factor, I, L, B, but now we have I hat crossed into K hat, okay? I hat cross K hat is equal to negative J hat, okay? Negative J hat. And this is just from the stuff I wrote down before here that we should all kind of have set to memory kind of thing. You can always remember it because it's kind of like a permutation, right? It's like I cross J equals K, and then if you slide everything over to the right one, well, K gets popped over to this side, and then it's K cross I equals J. Slide everything to the right again, J gets popped over to this side, and it's just J cross K equals I. Then if you flip them, right, flip the J and the I, pick up a minus sign. Flip the I and the K, pick up a minus sign. Flip the K and the J, pick up a minus sign. Or if you have other ways of memorizing this or doing cross products, that's fine too. Some people like to use determinants to do cross products, and if you've done linear algebra, maybe that's the way that you go with this. That's fine. Either way works for me. Okay. But bottom line is here we end up with this minus J hat contribution, right? And so we have the minus, oh, I have to be careful here. I made a bit of a mistake there. There is actually a minus sign here because we had minus I hat as our direction for our current, right? So this is really minus I hat for our L, right, from over here. So we should have a minus sign here, and because of that, these two minus signs are going to cancel, and we're going to end up with an F3 that's equal to ILB in the J hat direction. Okay, and if that minus sign part kind of confused you, just take a second to sort of absorb that. We have the segment of length here is going to be pointing off to the left, so we said it was in the minus I hat direction. Then I pull out that minus sign here, and so I'm just doing I cross K, not minus I cross K. So just I cross K gives us minus J. These minus signs cancel, and we're left with just J. Okay, so this is our contribution from that segment off to the left. And now we're only left with the contribution from that curved portion. Okay, so we need to be a little careful with how we handle this. Okay. So we can see that they did some nice drawing on here for us. We can see this thing has a radius r. They're already kind of suggesting that we should use polar coordinates, and I agree, it's definitely the way to do this. So if we look at our length segment dl, but we just want to look at the volume of it, so dl will have length. This is just the length of it. We're not worried about the direction that it points all the way around. So our dl is going to actually be r d theta, right? We can see that from the drawing here. We know that each of these little tiny length segments is going to be a length of r times the tiny little arc that we're going through. So it's going to be r d theta, okay? And now we want to sort of think about what direction is this cross product going to point. So as we're going around, we always have our dl is going to be pointing tangentially in this direction to our semicircle here, right? Like as we're going around, we're going to have a dl pointing in this direction, then it's going to point in this direction, as we see here. As we get over here, it's going to point in this direction, and so forth all the way around, right? So because our dl's are always going to point in that direction, and all the time we have our B pointing outward out of the page, you can right away use your left or your right hand rule, place the back of your palm, like the back of your hand, kind of in the direction where your fingers are pointing in the direction of DL, and then if you curve your fingers upwards, they're curving in the direction of B, and your thumb is always going to be pointing radially outward as you go around this thing, right? So we're always, no matter where on this semicircle we are, we're going to have a DF, an infinitesimal contribution to our net force here, pointing radially outward, okay? And that's going to be an important sort of factor as we do this. Let's worry only about the magnitude in the beginning, but let's remember that we will have all of these contributions pointing radially outward, right? And we're going to sort of bring that into play afterwards. So first of all, let's just write down our expression for each tiny little contribution to our force as we go around the circle. Okay, so our dF2, just to mean that we're on the circle here, is going to be equal to I dl, right, the magnitude that we had over here, times B. Right? It's basically just the same equation that we've used over and over again here, but now we have dLs instead of Ls, okay? dLs instead of Ls. And so what is our dl? Well, we can write dl as r d theta. So it's going to be I r d theta B, okay? So like this set of two terms here replaced our dl, okay? And now what we want to do is we want to break this up into contributions in the x direction and contributions in the y direction, right? So each of these little sections will have some contribution in the x direction, right? Like if you think of this vector, it has some x component and it has some y component. And as you crank it down over here, more and more of that contribution is going to be in the x direction until you're right here, and it'll all be in the x direction. Then you crank it up this way until you get right to 90 degrees, and then you're going to end up with all of it in the y direction. And then as you crank it back down, you're picking up more and more in the negative I hat direction, right? And so we need to write two expressions that we can integrate to take all of that into account. So we're going to kind of break this up into two parts. We're going to have a df2x and a df2y. And we want each of these to pick up the sort of character of us going through this angle theta from 0 to 180 degrees, and it's going to be picking up different contributions as we go through this angle, right? So for the x part, we're going to write I r d theta b, and this is going to be cos theta, and for the y contribution, it's going to be I r d theta b sine theta. Now think for a second about what this kind of does for us. As theta is 0, right? As theta is 0, we're basically going to have contributions for both, right? But as theta is 0, our cos goes to 1. We're over here, so all of our contribution is in the positive I hat direction, and that's exactly what we want. Do we have any y contribution at that point? When theta is 0, well, no, because sine theta is 0, and so we have no y contribution. That's exactly what we want. Then we're slowly turning things up like this, and when we get to this point, when we're at 45 degrees, well, cos of 45 degrees is root 2 over 2. Sine of 45 degrees is root 2 over 2, so they have the equal contribution, and that's exactly what we see here. It's kind of pointing off in a 45-degree angle, and we have equal contributions in both directions. It may not quite look like that on the drawing here, but you kind of get the idea. Then we keep cranking it up until we're at 90 degrees here, and then cos of 90 degrees is 0. We have no x direction contribution, but sine of 90 degrees is 1, and so we pick up all of our contribution in the y direction. And then as we're going back down through this, cos of stuff between 90 and 180 degrees is going to be giving us a minus sign on our y hat direction, right? So as we're cranking it down here, we're going to pick up all these negative contributions. And maybe now we can kind of see what's going to end up happening. Since this is symmetric about this line here, about our x-axis, or our y-axis, I should say, we're going to have this cancellation. All of the x contributions are going to cancel from side to side, right? Like the little contribution from here is going to cancel from here. The big positive x contribution is going to cancel the big negative x contribution from here, and all that's going to be left is the contribution in the j hat direction, in the y direction, right? But let's actually go through the integral and see how this kind of all plays out, right? So let's do that. We have our two expressions here, and now what we want to do is we want to integrate. We want to integrate over 0 less than theta less than pi, right? And why is that? Because we're doing a semicircle here, so we're going from theta equals 0, theta equals pi over 2 to theta equals pi. So the full 180 degrees, okay? And if we do those, we're going to end up with an f2x, which is going to be equal to I RB times the integral from 0 to pi of cos theta d theta. And what am I doing here? I've just taken this expression. I've factored out everything that doesn't get hit by the integral sign. So IRB and then cos theta d theta is all that's left in there. And if we do this integral from 0 to pi, we're going to see that by symmetry, this thing ends up giving us 0. This integral is actually 0. And so we get no contribution in the x direction, which is exactly what we expect because of that cancellation from left and right, right? And then in the y direction, we end up with an integral that looks like this: IRB, integral from 0 to pi, sine theta d theta. And if you do this integral, you're going to end up finding that this integral works out to be 2, and so you end up with 2 IRB. Okay. I've run out of space here. Yeah, I'll add a page. There's only a few more lines, but whatever. Okay, so we now have this contribution for f2 in the y direction. There is no contribution in the x direction, so it makes it kind of simple, right? We can write down our full vector f2 just as this magnitude in the j hat direction, so 2IRB, and it points j hat. If this was non-zero, there'd be some I hat component also, but there isn't, and so we just end up with this one sort of direction with a magnitude for our f2. Remember from above we had an f1 that was equal to 0, and we had an f3 that was equal to ILB j hat. Okay, and we also said that f is going to be equal to f1 plus f2 plus f3, right? So f is going to be equal to the contributions on each of these parts individually, all added up. So we now just need to add up all these contributions, and what do we get when we do that? Well, we get an f that's equal to, well, we're going to end up with an I and a b that we can factor out of both of them. So we're going to have I, b. From f2 here we have a 2r. From f3 here we have an L, and this all points in the j hat direction. Okay, and this is the expression that we're looking for. So the net force on that current carrying wire is actually IB times 2r plus L, all in the j hat direction. So all of it points upward in this j hat direction because everything that doesn't point in the j hat direction canceled out or ended up being 0 after all anyway, right? We can see that all the force on this segment of wire is in the j hat direction. These cancel out, so we only have stuff in the j hat direction here. And this portion of wire that goes into the page, well, the current is parallel to the magnetic field, and so as expected, it gave us no contribution at all, right? Add the whole thing up, and you find your answer there. Okay, so we'll leave this one here, and we will continue with force and torque on current carrying loops in the next video.